Good morning, everyone. Welcome to our presentation entitled Substation Grounding Designed for Safety. In this presentation, we'll be discussing about different topics. First one, the main differences between what we call safety grounding versus system and equipment grounding. Then we'll move on and mention a couple of standards and codes used in the substation system grounding and all grounding related design. Usually, the grounding design has to be performed through computerized program, which will be giving some information about it. Thereafter, we will be discussing about the main processes or steps in the engineering design of a substation grounding. And we'll take that by what we call starting points, when we have to start our design and how can we finish it. And at the end of this presentation, we'll be showing you an example using one of the softwares called WinIGS for substation grounding design. If you are in North America and you would like to comply with the guides or the standard used for the grounding design, you refer to IEEE Standard 80. Which is called Guide for Safety in AC Substation Grounding. And when I see AC substation grounding, this substation grounding can be applicable to transmission or distribution stations. At the same time, when we perform a design, you have to come with a couple of grounding testing. And this is using what we call IEEE Standard 81, Guide for Measuring Earth Resistivity, Ground Impedance, and ground surface potential of a grounding system. So there are different type of tests like you have to perform whenever you come up with a design. You're starting with a soil resistivity test, and once you come up with a design and you install it using the appropriate contractors, you perform a ground grid resistance, step and touch potential, and checking the bondings coming from all equipment or the fence to the installed ground grid. The main ways of checking or coming up with design or testing from a national perspective, let's say if you are in the United States, you use what you call the National Electrical Code or the National Electrical Safety Code. It has a couple of portions. For example, section 250, it will be discussing about all ways or appropriate ways of grounding and the minimum requirements for the installation. IEEE Standard 837, it deals with the connectors in the substation grounding. And when I say connector, that means the interconnection between the installed ground rods and the bare copper conductors, which has to be connected together. These kind of connectors can handle the maximum short circuit or grounding faults that happen in the substation in order to lower the mechanical and electrical stress on the ground rods and the bare conductors when the ground fault dissipates into the ground during the fault time. Also, having appropriate grounding design, it's a good way of protection of communication facilities for power station. In this case, you refer to IEEE Standard 487. If you do a grounding design for industrial or commercial power systems, you refer to IEEE 142. So this is not related to substation grounding. It's only for industrial and commercial. If you do a grounding design outside of North America, you refer to the European standard or the IC publication 479-1, which is entitled Effect of Current on Human Being and Livestock. So you have three different type of grounding. The first one, what they call a system grounding. The system grounding is the way you have your equipment are interconnected to the system. So it's a way of providing an adequate grounding reference and return path for ground fault so that the protection system for the substation can accurately detect or clear the fault. When I say detecting the fault, this fault detection comes through what we call appropriate microprocessor relays or electromechanical relays if you have an old system. And the way of clearing the fault comes through protected device, whether you have a fuse or a circuit breaker. So the system grounding can be like a grounding system which is an ungrounded, which is the old ways, or solidly grounded, which is the minimum requirements, or you can high resistance or low resistance grounding, or reactance grounding. The second type is what we call the equipment grounding, which is typically the bonding or the interconnection from the equipment to the existing grounding system or the ground grid. The third type of ground is called safety grounding. The safety grounding, usually like you'll be discussing about the substation grounding. When a fault happens, you're trying to minimize the voltage differences inside the substation, so you will not create any kind of fatal shock hazard, whether a step or touch hazard. Whomever is walking or touching anything within the vicinity of the station, inside the fence or around 1 meter outside. So once you know like the main ideas of grounding, you have to perform all your safety grounding design using computerized softwares. And the higher recommended one in the market are WinIGS and CDEX. The WinIGS like come from the United States and CDEX come from Canada. There's other programs related on the market. You will find different type of computerized commercial software such as ETAP, SKM, Easy Power, and other types. They have modules for grounding. Manual design design calculation for grounding is not recommended because it has so many assumptions and restrictions, and you better refer and use programmed software. So the main process of designing of a safety grounding, starting from soil characteristics. You have to measure the resistivity of the soil, or sometimes they call it the resistance. So like you measure the resistance coming from the soil, and from which you can calculate the resistivity. Second thing, like you have to know like how much would be the sizing of your conductor you're using for grounding. Mainly what we call conductor fusing calculation. You're trying to see how much would be the minimum requirements depend on the fault levels. Based on that, you're starting adding some ground rods and bare conductors or grounding electrode conductors in your system, and in order to lower the ground grid resistance and lower the levels of step and touch potential beyond or below the permissible limits. A couple of design factors affect the contribution or the way like you perform the design. How much like the available short circuit you have in your system. The higher the short circuit, the more cumbersome the ways like you do the design. How is your system configuration? Is it like a simple interconnection between one portion of your the grid to the ground, or it's gonna be an interconnected grid? What type of system grounding you have? Like let's say for a transformer or generators, whether solidly grounded or impedance grounded. Fault clearing time. The faster the fault clearing, the easier or the most safer in terms of designing. There is also like an X over R ratio, which is the amount of decay of the short circuit during the fault time. The surface covering, which is typically what type of covers like you will have over ground, whether like you put asphalt or gravel or crushed stones. The number of line coming into the facility or like the substation, and how many lines or feeders going out, and this is used in the calculation of what we call a split factor, which we'll be discussing later on. The outcome of the study at the end is to calculate three safety issues: the ground potential rise, the step potential, and touch potential. So let's start saying what we should do like at the beginning, which is the soil resistivity measurements. This can be done with different type of ways. The most popular one is called the 4-pin method or the Winner method, and you take different samples across the area of the substation, and you can use even other methods like you'll find in IEEE 80 or 81, and use like the aforementioned equation, which is the rho, which is the resistivity, which is typically a function of the resistance you calculate from the grounding tester, and A is the spacing between your probes. Soil resistivity can be affected by different factors One of them is the amount of salt like in the ground, the amount of moisture, and the temperature level whenever you perform the soil resistivity test. So the higher the percentage of salt in the system, like in the ground, the higher the resistivity you would achieve. The higher the moisture, the higher the resistivity. Whereas like the lower the temperature, the lower the resistivity you'll get. Sorry, the lower the temperature, the higher resistivity you will get in your system. So worst case scenario, like to perform like a soil resistivity test is during winter time, especially if you're talking about northern parts or parts like you will have very cold weather, such as in Russia or in Canada or Northern Europe. The second step in your design is calculate the conductor sizing based on the amount of current in kiloamps, and you can do that like using any power system study. The material used like for using the conductor, whether like you have a copper or aluminum or like a copper alloy, this is what we call the KF. The second thing, the duration of the fault in second. How much would you expect this fault would last in the system till being cleared? So once you perform like these two steps, you started like initiating or doing a kind of a conceptual design for a ground grid, adding some ground rods and bare conductors and create a mesh. Once you create this mesh, you're trying to see like how much current will be passing through the ground when a ground fault happens. Basically, when a fault happens like on your line, not all the current will be dissipated to the ground grid. A portion of the current will be going to what we call shield wires or a counterpoise, which is a grounding between towers or poles if existing, or any neutral going from the poles and interconnected to the ground. And this portion of the current not going to the ground, that will create what we call the split factor. And this split factor, you can use the IEEE standard charts, which are function of the ground grid resistance through your design, the number of transmission line in and distribution line out, and based on these curves you can calculate the split factor in your system. Out of your conceptual design and the calculation of the split factor and the current like passing through the ground, there's some definitions. The main one like for the safety is the ground potential rise, which is the potential of grounding structure with respect to remote earth during fault times. In other words, means when a fault happens, there is an elevation or a rise of potential or voltage of all structures like within the vicinity of the station compared to the remote earth, which is like a point way down in the earth, and it's not really specified how deep it is in the IEEE standard, and that happens only during fault time. So this snapshot showing coming from a software showing you the levels you would get across the station, because this GPR or ground potential rise is not a constant number, it's a gradient, it's fluctuating from one portion to another. Other portions for safety is step and touch potential. Touch potential is typically a lower voltage than the GPR, which is the potential difference between the GPR and the step potential at the point when a person is standing, while at the same time contacting or touching a grounding structure. So we can come up near like a transmission tower, touch it at the time when a fault happens. That will create what we call a fault potential, touch potential. And this touch potential, if you have a good grounding design, shouldn't really create a shock in your body. Whereas like if you're walking around this kind of structure during a fault time, you can create or like and you're bridging like with a distance of 1 meter between your legs without contacting any grounding object, you can be susceptible to what we call the step potential. And also with a good design, this step potential should not create a shock in your body. And the amount also like of step and touch potential are based on the weight of the person during like walking around the vicinity of the substation when a fault happens. The IEEE they're using two weights, 50 kilograms and 70 kilograms. The 70 kilograms provide higher limits of safety, so we will go for usually the worst case scenario, which is 50 kilograms. This is the one of the equation or the calculation of the touch potential, which is a function of what we call the derating factor, surface layer derating factor CS, and rho S, which is the surface material resistivity. The resistivity we can get it from the measurements using like a Wender method. The surface derating like factors we can from the different curves in the IEEE 80 standard. And this is just a snapshot of showing you the limits, maximum limits for step and touch voltage, whether you're using a 50 kilogram weight for design or 70 kilogram. The 50 kilogram will show, which is on the left side, will showing you lower level of permissible step and touch voltage. That means it's more, it's a worst case. Another step in the design is the ways of materials or grounding covering you use like to enhance the level of step and touch voltage limits within the vicinity of the station. The typical one used is the crush stones. The crush stones has an average resistivity of 3000 ohm meter. Then we will go like of trying to come up with more detailed design. Let's say like you're coming up with a spacing of a ground grid like 20 feet by 20 feet. You install your grounding 18 feet like below the ground. You use the appropriate grounding size based on the previous equations we have seen. Even like you're trying like to add extra grounding outside the fence, like 3 feet outside the fence, in order to protect whomever will be touching the fence, even if he is outside the station at the time when a fault happens. Ground rods, typical diameters of it is 3/4 of an inch or 5/8 of an inch. The lengths like typically are around like 10 feet. The material used for ground rods are copper clad for theft perspective, like you're trying to lower the theft by not using pure copper. And the locations, you can add some ground rods in the corners or within the vicinity of the station grounding grid. The surface covering, let's say like you use the crush stones, you put like around like 4 to 6 inches, and the material like what we call you can sometimes you use gravel or limestones, and you have to extend like the adding the covering then you'll be using like your WinIGS like or computerized software program, and add the information from your measurements of the soil resistivity, and from these measurements you can do an analysis for the resistivity layers. And these resistivity layers typically use what we call the two-layer method, with an upper layer, in this case 6.6 ohm meter, and lower layer which is higher, 51.33 ohm meter, and the height of the first layer is going to be 12 feet. And that would be the grounding layout in your system. Like you have a substation, you add like a different ground rods, which you will see here like in green, whereas like you have different bare conductors which you see in blue. Then you perform your analysis. Your analysis should cover the main safety, which is ground potential rise, step and touch voltages, and you will see that like with the calculations in the next slides. you will have from the calculation the amount of resistance of the ground grid is very minimal here, 0.0351. The amount of current or fault during this, like going to the grid, is 47 kiloamp. And the derating factor using the IEEE standard based on the layer thickness. The layer thickness that comes from the ground covering, you can calculate the CS, or the reduction factor. This reduction factor, you will use it in the calculation of the permissible step and touch voltage in IEEE 80. So the analysis using WinIGS will show you the levels of gradients of ground potential rise, and you see that in different colors. The blue one will show you lower level of, let's say, like 635 volts, and the highest level can show you more than 1550 volts. You'll see from the calculation on the top, the voltage maximum is 1.652 kilovolt. Touch potential or a touch hazard analysis. You will see also like levels of touch ranging from as low as 21.64 volt in blue, and the red one, which is the highest calculation of the or levels or gradients of touch voltage, 216 volt. But the maximum one you could get like from the design is 238, as you see from the top, which is lower than the permissible. That means like this design is good, so it's lower than 291 volt. Last step is using the in the design is coming up with the gradients of the step potential, which range as low as 18 volt and as high as low as 1.8 volt and as high as 18 volt, and those numbers are way much lower than the permissible voltage of 672 volt.